Hi, my name is Yixin Ye. I obtained my PhD degree in chemical engineering from Carnegie Mellon University in May 2020. The topic of my talk today is integrated optimization of design, storage sizing, and maintenance policy as Markov decision process, considering varying failure rates. The work was advised by Professor Ignacio Grossman and was in collaboration with Jose and Shiva from Lindy. Our motivating example is air separation units, which usually serves dedicated customer with gas products through pipelines. And the failure of any stages here is going to result in system failure and therefore interruption of pipeline supply. And in response to that, there are several reliability increasing strategies, including redundant equipment, inspection, maintenance, and liquid storage for gaseous pipeline products. And that begs the question of the trade-off between the costs incurred from interruption of pipeline supply and the cost in advance incurred by reliability increasing strategies. The currently used tools to address that problem is discrete event simulation tools, which can be time-consuming, labor-intensive, and most of the time cannot exhaust all of the options. So what we propose is a math programming optimization model, which provides a structured consideration of cost-gain balance, greatly reduce repetitive efforts, and covers entire searching space. So again, our goal is the integration of design and maintenance to optimize reliability in process systems that covers the decision regarding redundancy selection, maintenance policy, and tank sizes. The first major challenge we face is to capture the stochastic process of failures and the impact of maintenance. And then we have to embed the stochastic models into mathematical programming optimization, where we have to balance accuracy and tractability of the model. And in order to improve our performance in terms of tractability, we have to develop algorithms for larger scale problems. So in terms of the stochastic process we mentioned before, we take this assumption of the varying failure rates of bathtub shape, which is a widely accepted assumption. So that means the failure rate of a single unit has three phases: the initial infant mortality phase, and followed by the stable phase, and then followed by the end-of-life wear-out phase. If we discretize that and use the Weibull distribution to represent each of those phases, they'll have different shape factors. Here, beta 1, beta 2, and beta 3 correspond to the shape factor of these three phases. And with that discretization of the bathtub curve, we introduce the condition-based maintenance modeled as Markov decision process. So Markov decision process is basically Markov chain with an additional action space dimension. So in Markov chain, we have the probability of the system transitioning from one state to another based on the state itself. And in Markov decision process, that probability is also dependent on the action you take at each state. So here, we use the three phases from the bathtub curve at three states, and there are also the failure states and the standby state and the stopped for maintenance state that are to be incorporated for each unit. And so these arcs between the states are the actions. They include the inspection intervals at each state and the action of stopping it for maintenance, the action of maintenance, the action of repairing, and the action of do nothing. And they determine the system dynamics. They would decide the probability of the system going from one state to another. So the model looks like this. It's an MI/NLP model, call it DMP. It minimizes the capital cost and operational cost, and the decision variables are subject to certain logical constraints. And we formulate the Markov decision process optimal condition, aka the Bellman equation, as algebraic form. The And we also have to capture the stationary distribution of the Markov chain. That's like the reduced Markov chain after the action with the action of the Markov decision process selected. And we are modeling each stage. Here, stage means like compressors or pumps independently, but then we have to capture their interdependence with these constraints. So again, this is an MI and LP. So we first want to do some reformulation, like we want to reformulate the bilinear terms of the binary variables and continuous variables here, like this. So because it's binary, between binary and continuous, it can be linearized exactly. And another thing we did is we reformed the objective function. It was a straightforward value calculation of Markov decision process, but now we can replace it exactly with this one. So it's better bounded when relaxed, when the model is relaxed. And now we're left with this only one of this complicating constraint or complicating variable, whatever you call it. So this R pen here is really the complicating thing that's capturing the interdependency of all the stages. And our proposed algorithm is going to address that. So this is the custom algorithm we propose. It's an overview of the basic ideas. It has two phases, the enumeration bounding phase and the rewards iteration phase. So in the enumeration and bounding phase, we first enumerate over all possible tank sizes selections and define each one as a node. And we calculate the lower bounds and upper bounds of the objectives at each node by solving two MILPs. So they'll be solved in seconds. And as the calculation proceeds for each node, we can prune nodes whose lower bounds are greater than the upper bounds of any other node. So now we'll only have a few nodes left for the rewards iteration phase. And for each remaining node, we are going to iterate on this complicating variable we mentioned before until it converges. So the optimal solution of the node is the final iteration MILP solution. We still iterate through MILP models. And then the optimal solution is going to be obtained each node. And we determine that the overall optimal solution is the solution that gives the lowest objective function among all the nodes. And now let's look at a case study of the air separation unit. So this is superstructure of the example we're looking at. It has 4 processing stages, including the main air compressor, the pre-purifier, the booster air compressor, and the liquid oxygen pump. And it also has 2 storage tanks for oxygen and nitrogen, respectively. So if we only consider the design decisions, there are 60,000 combinations. And the optimal design looks like this. So 60,000 is already a hard number for discrete event simulation to cover all of them. But another result of our model is the optimal maintenance policy for each stages. Here's an example of the booster air compressor. So if we consider the decision made here, that's an impossible number of combinations to be covered by discrete event simulation. And although our direct solution of the MNLP only reaches about 20% gap after a day, the custom algorithm we proposed can solve it within 441 CPU seconds. And now a closer look at the custom algorithm, or a more graphical look. We have the nodes of different storage selections, and we solve the bounds of each node with a lower bound and upper bound MILP models. Now we can see that for these 2 nodes, they are actually pruned by this node because the upper bound of this node is lower than the lower bound of them. So now we only have these 2 valid nodes, and we're gonna do rewards iteration for them and pick the best stationary point for between them. So this is how it proceeded for the example we saw before. We can see that for the first node, we calculate the lower bound and upper bound. And then for the rest of the nodes of the first row, they actually produced lower bounds greater than the upper bound of this one. So the upper bounds are not calculated. We don't have to solve those models. And for this node, it's valid based on this one, but then these two are then pruned by the next node examined because it has a lower upper bound than the lower bounds of both of them. And then for the rest of nodes, they all have a lower bound that's greater than the upper bound of this node. So they only have to solve for the lower bound and not the upper bound. And now we can see that the lower bound and upper bound of this node is very close. So we can actually determine that the optimal solution of this node, which is the optimal solution of the entire problem, has a very, very little gap from the global optimal solution. So we can also look at computational results of a few randomly generated problems. Here are 20 problems of 4 stages, which are obtained through perturbation of the example problem. They are quite stable. And there are additional 26 stage problems, which are obtained by fabricating 2 more stages based on the original example, and also do some perturbation of the parameters. So you can see that in general, if you look at the average computational times, 6 stages is obviously longer than 4 stages. And it's also performing quite well because it's also within a few thousand seconds. So for conclusion, we proposed a new MI-NLP model to optimize redundancy selection, storage tank size selection, and maintenance policy based on Markov decision process. We took the assumption of bathtub curve for single units and break it down to 3 states, and also did some standard linearization and reformulation of the model to obtain better results. And based on that, we also proposed a custom algorithm of 2-phase, and which greatly improved the computational performance. So I'd like to thank my funding resources in SF, Lindy, and the Center of Advanced Process Decision Making at Carnegie Mellon University. And here are the references. Please come to me if you have any questions to the Zoom link. And I thank you for the attention.